Hello and welcome to our introduction to Chapter 5, Chemical Bonding. In this chapter, we are going to start building up our covalent molecules, things that have shared electrons. So we're going to be looking and focusing on our nonmetal section of the periodic table, and how do those nonmetals form bonds? How do they share electrons? We know that the sharing of electrons occurs in order to reach a stability, a noble gas electron configuration. But now we're going to be able to say, well, if this molecule exists with this specific molecular formula, what does it look like? All the way to from the connections through to the molecular shape. This is the endpoint for us as really building up the idea of quantum chemistry and being able to say structure is of the utmost importance when we want to take a covalent molecule, say as a drug, some sort of medication that we've created. The structure of that will dictate its function in the human body. And so when we're looking at these structures, really this is the end goal for a lot of chemists is to identify connections. So not only the idea of where the bonds are, what do the bonds look like, but then take it one step further and say, what does the molecule look like in three-dimensional space? So we've come from the idea of Lewis theory. Lewis theory is one of the simplest bonding theories. We used it in Lewis dot atoms. We used it in Lewis theory for ionic compounds. And now we're going to be able to use it for covalent compounds as well. Again, the overall idea is that it's the valence electrons that are able to go into reactivity, namely for our nonmetals, that's going to be the S and P electrons. Those outermost electrons are going to be the ones that we're focusing on. Now, if we know the valence electrons, we can predict many of the properties such as the stability, shape, size, polarity, things like how many bonds do those atoms make? And that's what we kind of talked about. I'm going to just write out a few of our nonmetals in row 2 and be able to do quickly their Lewis dot atoms. 1, 2, 3, 4 valence electrons for carbon. Nitrogen has 1, 2, 3, 4, 5. So it has 5 valence electrons. Oxygen has 6. Fluorine has 7. And neon has 8. Neon being the noble gas at the end of that row. Now, we know about the octet rule with ionic compounds, and the octet rule for ionic compounds symbolize the idea that those charged particles, cations and anions, were able to form because losing or gaining electrons to reach their noble gas configuration was stable. The same idea happens for covalent bonding. Typically, now this isn't always true because we'll see some exceptions today, but typically when we think about our covalent compounds, we can look at the number of valence electrons they have and predict how many electrons do they need to reach the octet, and that need tells you how many bonds they typically like to make. So carbon would have 4 more bonds. If you add those up, you reach 8. And that's what we called the octet. Nitrogen needs 3 more electrons, oxygen 2, fluorine 1, and neon, why noble gases don't react, is because they already are at their octet. That doesn't mean that noble gases can't be forced into bonding. They do have 8 valence electrons, and yes, that even though that shell is complete, they could still react those. We'll see a couple of those in class. But here's our typical idea where we could predict the number of bonds that would be stable in a molecule. So why do atoms bond? This is one of the major ideas behind chemistry. Chemical bonds form because they lower the potential energy between charged particles that compose the atoms. Now, if it's not an ionic compound, there are no charged particles. However, the same thing occurs. Chemical bonds form when the potential energy of the bonded atoms is less than the potential energy of the separated atoms. So whether you're looking at a charged particle or whether you're looking at sharing of electrons, overall, making bonds lowers the energy of the atom or the molecule. I'll call it the system. We've talked about the system before. It's of the reaction. It's of the thing we're focusing on. Making bonds lowers energy. What does that mean? In order to break bonds, you actually have to put energy into the system. That concept is sometimes mixed up, but think about it as little magnets, right? When we're thinking about our refrigerator magnets, we just put our magnets on the fridge and they stay there, they stick, right? That's a bond. There's an electrostatic attraction between those two opposite ends of the magnet. One's a positive pole and the other one's a negative pole. And so therefore, the magnet is stuck together once we bring them close together. In order to pull off a magnet, we actually have to go and put energy into that system. We are pulling the magnets apart. Atoms are the same way. There are nucleus to electron attractions, and that attraction holds those two species together. Now, in order to actually break a bond, we need to pull that attraction apart. So things that we need to consider, yes, there are repulsions, and we'll discuss what those are in just a little bit. But the overall idea of why bonding happens is because there is an attraction between opposite things. Now, it could be plus and minus charges, cations and anions, or it could just be the protons in the nucleus to the electrons in the electron cloud. And this overall idea of the attractions should be the greatest value. If we see that a bond forms, it's because the attractions outweigh the repulsions. Just to be able to describe a couple of those and to draw them out, let's first talk about ionic bonding. The simple one that we saw before, sodium becomes sodium plus 1 by losing an electron. Chlorine gains that 1 electron and becomes Cl minus 1. Now, when we put those two together, that's what we called lattice energy. And we made the wonderful ionic compound, sodium chloride. Now, if we think about a sodium cation and a chlorine anion, remember anions tend to be larger, cations tend to be smaller. There is an attraction between opposite charges. Overall, there's an attraction between the plus and the minus. Now, if we think about sodium plus 1, and its valence shell is empty. It's got some core electrons. We can draw a couple in there. 2 and 8, just to make sure it's the octet rule. And we can compare it to chlorine, minus 1. And again, we'll just draw a couple of core electrons. It's not going to be accurate. This is just to get the idea of opposites attracting. Well, we definitely don't have 9 more. In that valence shell, we'll put in the outer 8. There's that extra electron. Now, what's attracting? Literally, it's the nucleus of one to the electrons of the other, or the nucleus of one to the electrons of the other. That's attraction. But what's repelling? Well, I'll draw it in red just to make it look sad and bad. The electrons repel each other, and the nuclei repel each other. So nuclei to nuclei, there are protons in each nuclei, so the two atoms can't sit right on top of one another. They're not going to occupy the same space. Also, the electrons repel each other. They're not going to overlap and occupy the same space, which is why in the lattice structure, how we drew it was this alternating plus and minus, hugging each other, attracted, but not overlapping, still occupying their own space. Same thing with covalent bonding. We have the same idea. Now in a covalent bond, let's just look at something like fluorine diatomic. We briefly talked about these guys when we did our Lewis dot atoms, but there is an actual attraction between the protons in the nuclei of one and I'm just going to write the valence electrons here, and there's 7 of them, and the electrons of the other. Let's write out those little 7 dots for the valence. Now again, protons of one attracted to the electrons of the other, but there's also nuclei repulsion and electron repulsion. So we have to consider like charges repel, opposite charges attract. Now in Coulomb's law, what he tells us is that if opposites attract, that is energy releasing, exothermic, negative in value. If like charges are brought together, that is energy raising, positive, endothermic. Now, this doesn't necessarily mean good or bad, but we know that atoms bond to lower their energy, become more stable. That overall is a good thing. And so what we want to be able to think about is the reason why bonding occurs, whether it's ionic or covalent, is because the attractions outweigh the repulsions. If the repulsions are greater than the attraction, the bond doesn't form. And we see that there are some molecules that don't bond. And there are some theoretical things that we can calculate and say, would this ever form in real life, or can we make this form? Sure, but it's probably not going to be stable. It's probably not going to stay very long on the shelf. And that's because there's no attraction holding those electrons together with the protons. And so once we start looking at all of these ideas, what's important to note is all of the Coulomb's law that we have to consider. All right, there are 3 major types of bonds. We're going to discuss, again, just the 2. Ionic and covalent. We've discussed ionic bonds in the last unit. Electrons are transferred between atoms. A non-metal will gain electrons to become an anion. The metal will lose electrons to become a cation. Now, what we're going to discuss in this chapter is primarily covalent compounds. Between 2 nonmetals, electrons can be shared. There is another type of bonds. There's actually a couple more types of bonds, but they're not widely used in general chemistry textbooks, primarily because in general chemistry, we are just doing a basic breadth of knowledge and we're not really diving in too deep to anything. A classic one that this book likes to present is the metal-metal bond or a metallic bond. Electrons here are pooled, so you can imagine it being like a wave of electrons over a communal sharing of between metal nuclei. There is actually another type of bond I was just reading about. I'll present it in class, discovered in the late 1990s, mid-1990s, call it the mid-1990s. And what it's based off of is a charge shift type of bond. And it's theoretical right now. They're still doing some research, but it primarily exists with our diatomics. And so it's very interesting. I'll present it in class. But our focal point will be ionic and covalent. But I don't want you to think about this as a black and white subject. We are going to see the variations in the degrees between ionic and covalent. Sharing isn't always equal sharing, and how quick are electrons transferred, right? So don't just think about this too far into the categorical sense. Think about it as more of a discussion, open discussion. Now, this guy, I think he's amazing. This is Linus Pauling. Linus Pauling, an American chemist. Yes, he was a biochemist as well, and a chemical engineer, and a peace activist, and an author, and an educator. He had it all. I think he's phenomenal. I also think his smile is contagious. He had written more than 1,200 papers and books, which dealt with over 850 scientific topics. This is phenomenal. He is one of the founders of quantum chemistry and molecular biology. He was born in 1901 and he died in 1994. So after you were, before you were born, but well after I was born. And one of his most important contributions was his book, The Nature of the Chemical Bond. Now, I just want to give you some history of this amazing man. He won a Nobel Prize in chemistry in 1954 for his work on bonding and understanding bonding. And not even 10 years later, it was 8 years later, he won a Nobel Peace Prize for his work on peace, essentially. He was a peace activist. He married an American human rights activist, and together he worked towards nuclear disarmament, which in my opinion is a very important thing in our day and age. Using chemistry for warfare is not high on my priority list, and it wasn't high on his. He wanted chemistry for the sake of helping people. And so the whole nuclear craze that occurred when a lot of our scientists from in the quantum realm provided information in the scientific field into the wrong hands. And Linus Pauling was one of those who promoted nuclear disarmament, not using nuclear warfare on humanity. So he's only one of 4 individuals to have won more than one Nobel Prize. He's the only one who didn't have to share his Nobel Prizes. He did a lot of work solely by himself. And he's only one of 2 people who won 2 Nobel Prizes in 2 different fields, because he won one in chemistry and one as a Nobel Peace Prize. The only other person that did that in 2 different fields was Marie Curie. And so his work, Linus Pauling's work in chemistry, led the way to a lot of concepts that we're going to be dealing with. Now, he was not the one who developed the idea of the Lewis structure, which we'll deal with, but he was the first person to identify a good definition of a covalent bond. He works with orbital hybridization, which we will talk about in Chapter 6. And what we'll see in this section is electronegativities, talking about how a covalent bond might not be an equal sharing of electrons, and there's a degree of sharing dependent on what two atoms are participating in those bonds. He also worked on biological structures of molecules, showing the importance of the alpha helix and beta sheets in proton secondary structures. His approach was that he used combined methods and results from X-ray crystallography and molecular model building, and with a basis of quantum mechanics and quantum chemistry. He actually was the one who inspired the work of Rosalind Franklin, who's my absolute favorite scientist in the world. She was the first developer of the structure of DNA. She did not win the Nobel Prize due to the fact that she died early in life due to ovarian cancer because of the X-ray crystallography, the X-rays, which is very, very sad. She also had a lot of her work stolen by Watson and Crick in the early 1900s due to the fact that she was a woman scientist. So I look at this guy as really a inspiring story of promoting science and promoting the cooperation for all scientific minds to come together and save humanity. And I think he's just an amazing person. Now, what did he do for chemistry? Let's go back to chemistry. When he was starting to do his work on the nature of the chemical bond, which has been called, if I might just add one more historical fact, which has been called the Bible of chemistry. He noticed that there was a difference between these single bonds in terms of how much energy was released when they formed. So he studied what we call bond energy. We will get into a good definition of bond energy and what it does, but it has to do with the amount of energy released when a bond is formed. The bigger the number, the more stable the bond is. And so what he looked at was he compared the numbers of H2, hydrogen diatomic, and F2, fluorine diatomic. And he looked at these two numbers and he said, you know what? I'm going to predict that if a covalent bond is an electrons pair being shared, these are both single bonds, 2 electrons are being held right here, 2 electrons are being held right here, that he predicted, or what was predicted at the time, was that the bond energy of HF would be exactly average, 296 kilojoules. Linus Pauling did the work and discovered a very remarkable outcome. That is not related at all. The bond energy, the amount of energy released when HF forms, is 565 kilojoules. And so what he started to say and predict was that HF has some ionic character. And that there is something about the electron attraction and the electron repulsion going on in HF, and he'll start to call this polarity. Now, polarity is going to be a very, very big topic for us in chemistry. Now, bond polarity. Most bonds have some degree of sharing when they are covalent bonds, and some degree of ion formation in them. So in life, we're not black and white. We're not just ionic or just covalent, and it's just one thing or the other. There's a very gray area of degree of ionic or degree of covalent. Bonds are classified as covalent if the amount of electron transfer is insufficient for the materials to display the classic property of ionic compounds. So just because we label something ionic and we say that typically that's a metal and a non-metal, that doesn't necessarily mean that there is an equal sharing of electrons. There's not enough energy to transfer the electrons fully, but there might be some degree of transfer. So if the sharing is unequal to produce the dipole or the actual ions, right? Think about those little magnets, the plus charge and the minus. If there is an unequal sharing to produce the dipole, it starts to look like ions. And instead of classifying it as ionic, we're going to start classifying it as polar covalent. So it might look like ions, but we'll still be able to say, yeah, it's covalent, they're shared, but they're not equally shared. One atom holds the electrons tighter than the other one does. So in covalent bonding between unlike atoms, that results in an unequal sharing of electrons, that usually means one atom is pulling the electrons closer to its side. That means that that one end of the bond has a larger electron density. So that results in the polar covalent bond. The bond is polar. It will have a partial negative and a partial positive charge. We'll be able to see what that looks like on the next slide. What I wanted to get into just briefly is that idea that if an atom pulls the electrons more, let's just say atom X versus atom Y. And let's say that atom X likes the electrons more, and so they start shifting over to him. Atom X is going to have a partial negative charge. That partial negative, again, isn't a full negative. It's what we call a delta minus. Delta is that lowercase d, Greek letter. It just means that the element X must like electrons more than element Y. Element Y is feeling a little bit electron deficient. It's not getting its full octet. It's losing a little bit, and that's what we call a partial positive. So this is important, especially for organic chemistry and biochemistry, when you start getting into reactivity. We won't see reactivity at all in this unit, but what we will be able to do is look at a molecule, identify whether the bond is polar covalent, and identify which end of the bond has a larger electron density, who holds the electrons more. That would be the partial negative side. And then who is electron deficient, who has the partial positive side. So it's all about identification for us. Now, electronegativity is a much better periodic trend. It kind of takes over for electron affinity, right? Remember we talked about electron affinity being really weird and wonky and saying that there really was no trend going down a group. Well, now what Linus Pauling was able to describe and to plot out for us is a unitless value that explains the idea of electron attraction. The higher the electronegativity, results in an increased attraction to electrons. That means that the atom would want the electrons more. The element that we see that has the highest electronegativity is fluorine. If we zoom in on this chart, which you will always have, all of our electronegativities, if we wanted to slap a value on it, you would have it. But the periodic trend, you should know. You should understand why this occurs. So we're going to dive into a little bit of periodic trends again, just specifically focusing on electronegativity now. So if we look at fluorine, he has the highest electronegativity on our chart, 4.0. Again, unitless value. The higher the number, the more likely that you want electrons. Why? Why is fluorine the most electronegative? Well, he has the highest Z effective, and that Z effective tells us that he pulls the valence electrons the most, and he is also the smallest in the row. right? So when we're thinking about where those valence electrons are, they are closest to the fluorine nucleus. And fluorine has the highest Z effective, pulling those valence electrons in. He only needs one more electron to reach his octet. And so he has that desire, that drive, that desire to get that extra electron to reach the noble gas configuration. In general, what we see is if we go down a group, N, remember our principal quantum number is increasing, and so therefore we see electronegativity decreasing. As we hold the valence electrons further and further away from our nucleus, their attraction, their desire to reach an octet is lowered. As we move from left to right across a period, again, the Z effective is increasing, and so therefore the desire to reach the octet is increasing. So electronegativity increases as well. Francium way down here, I'll change that color. Francium way down here has the lowest electronegativity. He is the largest atom with the smallest Z effective. So this is opposite of the trend for atomic size. That's what we can start to think about. Noble gases are not assigned electronegativity values because they already have their octets. Doesn't mean they can't react, but they just will not go into our discussion of bond polarity. So electronegativity, the ability of the atom to attract bonding electrons to itself. That's what we want to be able to see. The larger the number, the more likely that atom wants electrons. Now, the larger the difference in electronegativity between two atoms in a bond, the more polar the bond is. And so what we actually get to start to calculate is the change of electronegativity between the two nonmetals. The more difference that is, the larger the value. It will be an absolute value. We're not going to look at positives or negatives. Just take the biggest one minus the smallest one and say, what's the difference? The more likely that bond will be identified as polar, leading towards the actual ionic scale. So we can look at this. This would be between H and F, the molecule that Linus Pauling was looking at. The electronegativity of fluorine is 4.0. The electronegativity of hydrogen is 2.1. So that change in electronegativity, 4.0 minus 2.1, again, biggest minus the smallest, 1.9. And what we see here is that fluorine has the delta minus, hydrogen has the delta plus. We can draw this dipole arrow. It always points towards the atom that has the delta minus, and it has this little positive symbol down at the other end where the atom that is electron deficient, who has the delta plus. Electronegativity and difference in bond type. If the difference of electronegativity is 0, equal sharing, so things like H and H2, the change in electronegativity there is 0 because those two atoms are identical. That is what we call pure covalent. Now, if the difference between electronegativity is somewhere between 0.1 and 0.4, the bond is not polar enough to see any sort of uneven sharing of electrons, so we call that non-polar covalent. The typical example will be carbons to hydrogens. Carbon is a 2.5. Hydrogen is a 2.1 in electronegativity. So overall, their change in electronegativity is a 0.4. That's what we call a non-polar covalent molecule. That would still lie in the idea of equal sharing of the electrons in the atom. Now, if the difference of the electronegativity is between 0.5 and 1.9, that's what we describe as polar covalent. That is something like HF, or even HO. Oxygen, if we look on that electronegativity chart, is 3.5. Hydrogen, again, 2.1. That difference 1.4. Polar covalent, unequal sharing of electrons between the atoms in the bond. Now, if the difference between the bonded atoms is larger than or equal to 2.0, that's what Linus Pauling defined as ionic. And so when we look at this idea of metals and nonmetals, we start to see that it's not the best definition of bonding. This is a more accurate definition of bonding, looking at the actual desire or the ability to attract electrons in a bond and say, is there enough change in electronegativity to transfer electrons, or just to provide an unequal sharing, or just to provide a perfectly equal sharing of electrons. So when we look at our continuum of bond types now, we can, yes, identify what we predict based off of metal and non-metal identities, whether a bond will be covalent or ionic. But when we want to talk about this continuum and really understand the prediction, electronegativity is the best. The change or the difference in electronegativity really defines the type of electron idea. Are they shared? Are they equally shared, unequally shared, or are they transferred? Some bonds have what they call dipole moments. We won't spend too much time on dipole moments, but what we will see again is the change in electronegativity is going to be directly proportional to the actual measured value in that bond of dipole moments, the polarity idea. A dipole is a material with a positive and a negative end, similar to a magnet. A north pole and a south pole, and it's directly proportional to the size of the particle charge, or the size of the partial charges, and directly proportional to the distance between them. So it has to do with bond length as well. These aren't identical to changes of electronegativity, but they're proportional to the changes in electronegativity. We won't spend, again, too much time on dipole moments. You should know that if there is a polar molecule, it will have a dipole moment. Now, writing Lewis structures. This will be one of the most important processes that we do in this unit. If you do not understand or struggle with Lewis structures, you will struggle with the rest of the unit in terms of identifying what the molecular structure looks like in three-dimensional space. So what we do want to do in writing Lewis structures is follow a couple of steps, a guideline, if you will, or a process in order to be successful. The first thing that we want to do is predict the skeletal structure from the molecule formula. So you will always be given the molecular formula, and you want to predict what is happening. The best question to ask yourself is, which atom goes in the middle? Which atom is the central atom? To answer that question, what we want to be able to say is, who makes the most number of bonds? Now, we know from what we decided from Lewis.atoms is that carbon makes more bonds than nitrogen. Nitrogen makes more bonds than oxygen. And then oxygen makes more bonds than fluorine. As we look at the number of valence electrons, as valence electrons increase, the number of bonds decreases. So we would never really want to put fluorine in the middle when we could put oxygen in the middle. The second rule that we want to be able to do, once we start predicting who's in the center and getting some sort of idea about the structure based off of what we know in bonding, we need to calculate the total number of valence electrons. Now, we only want the valence electrons because those are the ones that go into bonding. We don't need core, we just need the total valence electron count of all the atoms provided in the structure or in the molecular formula. Then we want to be able to distribute those valence electrons, giving out octets, if we can, to outer atoms first. Why we want to do outer atoms first is just a little rule of thumb. You can do whatever atom you want, but we want to try to get the octet first, because what we'll start to be able to see is that the central atom will be able to dictate if they need any double bonds, triple bonds, or if everybody's just a single bond. The last couple ones that we have, again, give double and triple bonds. If necessary. We'll identify what that means, and then we'll do a check. We're going to be able to say formal charge here. We'll learn what that is. And resonance. We'll learn what resonance means. We'll start with looking at simple Lewis structures that really only need numbers 1 through 4, and then we'll get into the more strict Lewis structures that require number 5. So here's our first molecular formula. We're going to start with CH4. So predict the skeletal structure. Which atom is going to go in the middle? And we will always have one central atom for our discussions in this class. Yes, you can build up and get more than one central atom. We'll get there, but not right now. When we look at CH4, what we want to be able to say is carbon makes the most number of bonds, so I'm going to put carbon in the middle. Hydrogens then would go all around the outside. Now again, Lewis, simplification. Just put them somewhere. We're really just getting connections here. That's step number 1. Step number 2, count up the valence. Carbon brings 4 electrons to the table. Hydrogen brings 1, but there are 4 hydrogens. So that's a total of 8 electrons. Wonderful. Step number 2, done. Step number 3, start to distribute these 8 electrons. Now when we distribute, we want to do 2 electrons at a time. The reason for that is because electrons pair themselves, 1 from each atom. Now what Lewis did was he understood, yes, I'm grouping all of these 8 electrons together, but when I distribute them as pairs, that really understands the idea that 1 electron from each atom is coming together to be shared. If I put 2 electrons together and I want to call it a bond, we draw it as a line. There are 2 electrons here between carbon and hydrogen at the top, 2 electrons being shared between carbon and hydrogen on the right, 2 at the bottom, 2 on the left. There are 4 single bonds. 1 to each, carbon to hydrogen. Lovely. Now, here's what I want to say. Do I need to do double or triple bonds? Well, I've distributed all my 8 electrons. Check. Does everyone have their octet or their duet? That's what we want to be able to say. Hydrogen needs a duet to reach its electron configuration, that of helium, with 2 electrons in the 1s orbital. And carbon needs an octet. So let's go ahead and double check. Hydrogen, 2 electrons. Yep, everybody's got 2. Carbon, 1, 2, 3, 4 bonds. 2 electrons in each, 2 times 4, 8. Lovely. Everybody's set and ready to go. Let's do another one before we get into exceptions. CH2 Oh, now, who's going to be in the middle? That's carbon again. This time we'll have oxygen, hydrogen, and hydrogen. Again, just put them around. Give them some room. If you even want to say, hey, can I spread these out even more? Sure, of course. Why not? Give them as much room as they need, right? So that your structure looks clean and not really messy. All right, count up those valence electrons. 4 from the carbon, 6 from the oxygen, and 1 each for the hydrogens. 12 electrons total. Let's go ahead and start distributing. 2, 4, 6. Now, when I want to do my distribution, number 3, to the outer atoms first, I know that I've done 6 electrons in my bonds. So I have 6 electrons left over. Both hydrogens have their duet. Now let's focus on oxygen. 2 electrons can be put in as a lone pair. It's to fill the oxygen's octet. 2 more, 2 more. Now that oxygen, let's count up the electrons it has around him. 2, 4, 6, 8. Wonderful. We have the 8 electrons around oxygen. So we've distributed, again, we've also distributed all of our electrons. We distributed 6 more. So if we were to count 2, 4, 6, 8, 10, 12 electrons total in this molecule. But let's look again and say, now we have to move to number 4. Do I need to give double or triple bonds? Well, the only way to answer that would be to say, does everyone have their octet? No, carbon doesn't, but I don't have any more electrons to give. So instead, what I have to do is I have to get rid of 1 lone pair and share it between the oxygen and the carbon. So what that means is that the oxygen and the carbon has what we call a double bond. Hydrogens to carbons are going to be single bonds. And when we look at what's left over on the oxygen, these are our non-bonding lone pairs. They are not bonding because they are not held between 2 atoms. They are solely on the oxygen and only the oxygen. That one's gone. I like to erase it and to make it all clean at the end of the day. So we can start to see how carbon can now make a different type of bonding. 2 single bonds and 1 double bond. But what we identify at the end of the day is that carbon still makes 4 bonds, right? A double bond and 2 single bonds adds up to 4. 4 bonds total. 1, 2, 3, 4. 1, 2, 3, 4. Excellent. We'll have a lot more practice with Lewis structures and getting through these rhythm of going through and double checking and finding this writing of Lewis structures as a second nature. Before we get into formal charge and resonance, I want to go through a couple of exceptions to our Lewis structure theory and why Lewis structures don't always work. There is a class of molecules called radicals. A typical example is NO, not no, nitrogen monoxide. Radicals are investigated, no double O there, nitrogen monoxide, are investigated in organic chemistry. They are investigated in biochemistry as well. Free radicals in our body, things that are bad, that we could inhale. Polycyclic aromatic hydrocarbons, PAHs, are are a byproduct of combustion, so cigarette smoke or car exhaust, has a lot of PAHs. These PAHs can get into our lungs and then cause radical reactions with our tissue, with our DNA. And so if you've ever heard of antioxidants or free radicals or that whole class of why you should eat blueberries or acai berries or any of those things, it's to mitigate any of these side reactions from these PAHs or from other things in our atmosphere that can cause distress in our systems, such as things like cancer. Radicals don't work for Lewis theory. Why? Well, if we think about nitrogen and oxygen making a molecule, there's no central atom because there's only two elements here. But once we start thinking about adding up our valence electrons, big old shock. What do we do with 11 electrons? Lewis doesn't know how to deal with that. Putting 2 electrons in at one time doesn't add up to 11. And so radicals don't form for us. Now, if you wanted to see how we get by with that, yep, we can put 1 electron in. And so when we look at that molecule, it does have a structure. It doesn't mean that it doesn't exist. It does exist. However, radicals don't truly follow our idea of Lewis theory and Lewis structures. Another one that wasn't necessarily identified with Lewis theory is incomplete octets. Can't spell octets today, but that's all right. Incomplete octets are going to be with atoms that do not need 8 electrons, primarily boron. Boron is our classic example of an incomplete octet because he only has 3 valence electrons. Now we'll see that it follows Lewis theory. We can draw a structure. It's just an exception to our octet rule that we said way up here. We want to distribute electrons to give an octet. Well, we don't need to for boron. Boron does make more bonds than hydrogen. Hydrogen only needs 1 valence electron to complete its duet. Boron is special. When we think about boron, we can say he brings 3 electrons to the table. Each of our hydrogens brings 3 more. Notice we won't reach an octet. An octet is impossible because we only have 6 electrons. And so when we see boron in this form, we know that an incomplete octet will be found. Anytime you see boron, he doesn't need his octet. He can have one. We'll talk about formal charge in a little bit. But with boron in its neutral form, he's quite happy right here. 3 electrons makes 3 bonds, incomplete octet. When we talk about formal charge on the next slide, we'll talk about why is that okay. Expanded octets also occur. Oh boy. With expanded octets, 3rd row elements or below can expand their octet. 3rd row, 4th row, 5th row on the periodic table, all of those can do this expansion of their octet simply because when we are looking at their bonding, they have something special. And that, what we're going to see at the end of this discussion, are going to be those d orbitals. I'll have a little bit of a spoiler for you right now, just so that we can explain why the 3rd row and below can do this. The one that I'm going to look at is going to be H2SO4. Actually, let's do Let's do this one first because I like H2SO4 for my next example. Um, with H2SO or with SF6 sulfur hexafluoride, sulfur goes in the middle. He makes the most number of bonds. Typically, he would make 2 bonds. That's what we would predict he would need to make. But what we see here, when we count up the valence electrons, my 7s are funky, is that we get a ridiculous amount of valence electrons. And so technically, the total number of valence electrons here is 48. We'll see quite a lot of dots. Now, fluorine is in row 2. Fluorine can never expand his octet. Sulfur can expand his octet because he has the miraculous n equals 3 principal quantum number for his outermost shell. When we know n equals 3, L could equal 0, 1, or 2. And so technically, even though sulfur's valence electrons only go up to the p4, the 3p4 orbital, we still have the d orbitals available. So 2, 4, 6, 8, 10, 12 electrons go into bonding. The other ones go into the non-bonding lone pairs on the fluorine atoms to fulfill the octet. When we look at this expanded octet, again, we'll identify in our next slide why it has to do for both of these, why these still work, incomplete and expanded octets still work, simply because when we look at the resulting structure, we get to double check with something called formal charge. Resonance and formal charge are 2 additional concepts to write the best Lewis structure possible for a large number of compounds. Now, for a large number of compounds, primarily the ones that have a lot of electrons, like our last one, when we get up to 48 electrons, the idea of double and triple and expanded octets becomes more readily seen. Resonance is used when there are 2 or more valid Lewis structures, and we can start to identify which one's the best, or are they equal. Namely, that comes when we have double or triple bonds. Formal charge, which is what we'll talk about first, we'll be able to use for any structure that we want to determine if it's correct. It's a bookkeeping that allows us to look and say, did I do everything correctly? What we want to be able to see with formal charge is that we've distributed the electrons evenly based off of the element. If oxygen brings 6 electrons to the table, did we give him 6 electrons in the structure? If carbon brings 4, did we give him 4? Things like that. And so formal charge, even though the molecule itself is not charged, a formal charge can tell us that there are charges existing in the molecule. They just overall add up to 0. We'll start with formal charge. The concept of formal charge is useful because it helps distinguish between competition and skeletal structures, or even competing resonance structures, when we'll see what resonance is in just a little bit. In general, these 4 rules apply. The sum of all the formal charges in a neutral molecule must be 0. So if I had a neutral molecule, which I'll show you in just a little bit, however, it's even though the overall charge is 0, that doesn't necessarily mean that there aren't any formal charges. Overall charges of +1, -1, +2, -2, We tend to see smaller charges. Plus ones and minus ones are very common. If you start seeing the plus twos and minus twos, then you might have done something weird. But overall, formal charges should equal the charge of the overall molecule. So that's number 2. If we have an ion, a polyatomic ion is what we're going to be able to see in our examples. The sum of all the formal charges of the ion must be equal to its overall charge of the ion itself. Small or 0 formal charges are better than large ones. Zeros and plus ones or minus ones are better than plus twos or plus threes. And when a formal charge cannot be avoided, the negative formal charge should reside on the most electronegative atom. And that's what we'll be able to say in resonance structures. Can we start to distinguish differences? Overall formal charge is calculated this way. The number of valence electrons that the atom brought to the table. Again, it's based off of individual atoms in a Lewis structure, minus the number of non-bonding electrons. These are our lone pairs. So add all those up, and a half of the bonding electrons. This is how your book uses it. I also tend to just say count 1 for every bond that we have. So we'll practice. I like looking at this one first. Ozone. We've talked a little bit about ozone before in class. It's that molecule in the atmosphere that is currently depleting due to climate change and greenhouse gas effects and all of those lovely atmospheric chemistry topics that we can talk about. Overall, O3 is a neutral molecule. There's no charge up here in the top right-hand corner. We can add up all of the electrons. 3 oxygens means 18 electrons total. I put 1 oxygen in the middle, put the other ones around it, and we distributed some electrons. Now, this is the Lewis structure that I came up with, but what I see is that there's a lot of different looking oxygens, and is that okay? Let's just make sure that everyone has their octet. The oxygen on the right has 1, 2, 3, 4 lone pairs, 1, 2, 3, 4 bonding electrons, octet. And if we checked all the other ones, yeah, we have an octet. Now, when we look at these 3 different oxygens, though, we see something quite different. This oxygen has 2 lone pairs and 2 bonds, a double bond. This oxygen has 1 lone pair and 3 bonds total, a double and a single. And this oxygen has 3 lone pairs and 1 bond, a single. So now what we're going to be able to do with formal charge is be able to say, well, is this the best? Does this make sense? Did I goof? Did I mess something up? All 3 oxygens look different, so they should have a different electronic effect on each other. And so let's start with the one over here on the left-hand side. Formal charge for this guy is equal to the number of electrons brought to the table, that's 6, minus the number of lone pair electrons, 4, minus half of the number of bonding electrons, or just the number of bonds, 2. Overall, a 0 formal charge. Does that make sense? We know that oxygen typically makes 2 bonds. And that is what we see here. So this should make sense as a formal charge of 0. This oxygen on the left is neutral overall because he has his typical bonding. He brought 6 electrons to the table. We've distributed 6 electrons evenly around him, 4 lone pair electrons and 2 electrons in the bonds. Now the middle oxygen, for his formal charge, he brought 6 electrons to the table. He owns 2 electrons in that lone pair, and he owns 3 electrons, 1 from each of the bonds. That overall 6 minus 2 minus 3 is a +1. So right up here, we would put a +1 above that oxygen. He has a +1 charge. That's not a delta, that's not a partial, that's an actual +1 charge. What does that mean? In this Lewis structure, we have polarity. We actually have in here an unequal distribution of electrons, which causes a charged area. Last oxygen, the one on the right, he brought 6 electrons to the table. He has 6 electrons in lone pair electrons and 1 bond, -1. -1 over there on the top. Now, these charges have to be written. Formal charges absolutely always should be your last step in determining a Lewis structure. You have to do it for every single atom so that you know the actual charges on those atoms. When we look at those charges, you need to put them somewhere around the atom that they belong to. So when we're looking at an alternate view of what this molecule could look like, we don't have to write in zeros, thank goodness, but any non-zero formal charge we do have to write in. You can write it on the top, you can write it on the bottom, you can write it on the side. You can even not write the ones, right? If you want to just do that. Sometimes in organic chemistry, we circle them. That's okay too. When there are more than one, you have to write the charge for them. The value +2, -2, you would have to do that. But these are just alternates for us. The other one that I want to talk about is SO4 -2, the polyatomic. When we look at SO4 -2, sulfur and oxygen belong in the same family. So when we think about their typical bonding, each one typically makes 2 bonds. So who gets to go in the center? Well, when we think about sulfur being in the 3rd row, we know expanded octets can occur in the 3rd row. And so sulfur gets to be put in the middle due to that reason. Now adding up 6 electrons times 5, that is 30 electrons. One other thing why I like this example is this -2. The polyatomic ions give us a molecular formula that's charged. You have 2 extra electrons when you have an anion with a -2 charge. So think about what that charge means. A -2 means you have 2 more electrons, and therefore 32 electrons are there. We'll do 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I'll double check and say, yep, I've gotten all of my octets. Everybody has an octet, but let's look at formal charges. All the oxygens look the same. So if I calculate one, I know the other one. And it's going to be the same from up here. It's going to look like the guy on the right-hand side when we had 3 lone pairs and 1 bond. Same formal charge. Those repetitious things should be noticed. Oxygen brought 6 electrons to the table. It owns 6 in lone pairs and it owns 1 in bonding. So there's a -1 charge on all of these oxygens. Well, I knew I was probably going to have some charge, but my goodness, there's some -1s all over the place. Now for the sulfur, formal charge here, sulfur brought 6 to the table. It owns none in lone pairs, and it owns 4 in bonds. That's a +2. Yikes, yes, that adds up overall to -2. However, we know that this probably doesn't make a lot of sense because we like formal charges of 0. We hope that we put in the right number of electrons. What formal charge tells us here is that even though it might not have been obvious, sulfur needs to expand his octet here. This is not always the case. Formal charge of sulfur is the main idea here. Being a +2 should be a warning sign that this is not a valid structure. So instead, what we should do is start sharing electrons. When we start sharing electrons, what we actually end up doing is changing the formal charge. And we start to decrease the number of formal charges existing in our structure. Here, when we donate and have 2 double bonds, one between the oxygen on the right and the oxygen on the bottom, again, I just chose 2. All of them are oxygen, so any 2 you want to choose. It removes 3 formal charges, namely the +2 from the sulfur and the -1s from those 2 oxygens. Now we have only 2 atoms with a formal charge, and those are the top oxygen and the left oxygen, both with a -1. This is important. This is the best Lewis structure we have because when we look at the count of formal charge, we've reduced the count by redistributing some of those electrons within the structure. We still have octets for everyone. We just now see that the expanded octet notion stabilized the molecule by removing some of the formal charges. We'll bring SO4 - 2 back again when we talk about resonance right now. Now, resonance structures have the same connectivity, meaning the same atoms are connected, just only difference is that single or double or lone pair counts can change. Resonance structures must have the same number of electrons. Second row elements have that maximum of the octet roll. Third row elements can have expanded octets. Formal charges must total to be the same. Now, if the resonance structures have the same formal charges, then we just call them equal formal charge or resonance structures. And we'll see that with SO4 - 2. I'll show you a couple of different options that we could have drawn. But if you start seeing that some formal charges have fewer, or some resonance structures have fewer formal charges, then what we can start to see is that some resonance structures are going to be better than other resonance structures. The best example that we have is looking at SO4 - 2 first. So if we pop down and bring our example right back here, a lot of you could have probably said, well, why did you choose these 2 oxygens? Was there a reason? And the answer is no. I could have chosen any 2 oxygens to make my formal charge decrease. So if you drew this structure for SO4 - 2, you would have had what we call a resonance structure. Polyatomics are one of the easiest ways to draw a resonance structure. It's an alternate structure that says these are identical. I'm not going to use a yield sign. I'm using these double-headed arrows as my resonance arrows to say any 2 oxygens, doesn't matter which 2 I choose, any 2 oxygens can have that double bond with the sulfur. And the other 2 oxygens will have the formal charge of -1. These are all equal resonance structures because every one of them has 2 sulfurs double bonded to oxygens and 2 oxygens with -1 charges. So there's nothing different about them. So we'll call them all equal, and even you can draw more, right? There's going to be multiple different variations of this one. Another resonance structure that we can think about, we'll do this one first before we get there, is for the molecule CnO-1. When we start thinking about this molecule, carbon makes the most number of bonds. Nitrogens and oxygens can be on either side. So we have a basic structure. Carbon brings 4 electrons, nitrogen brings 5, oxygen brings 6. That's a total of 15 electrons, but don't forget that -1 charge, plus 1 more, 16 electrons total. 2, 4 go into bonding. We make those connections first. 6, 8, 10, 12, 14, 16. Now what we can start seeing is, okay, yeah, we need to make some double and triple bonds. How would I know? Well, I could look first to the octet rule and say carbon doesn't have it, or I could look to formal charges and say this is a -1, this is a +2, and this is a -2. No, minus. Yeah, -2. I did that right. Math. So when we're looking at this, we know that we have to give some more to carbon. So the first thing I'll do is let's just share. Let's share one there. And what that gives us is a little bit better scenario. -1, +1. Let's share from the oxygen. Let's just share evenly. Maybe you guys think, yeah, let's start there. And that would give overall this structure. Well, that's great, right? Nitrogen having a -1 charge, carbon being neutral, oxygen being neutral. Quickly do those formal charges. But then what I could propose is, well, instead of that, does this fit? What if I just wanted all of the electrons to be shared from oxygen, not one from either side, but all of them from the oxygen? Or what if I wanted the nitrogen to share and do all of those bonds? Here are 3 resonance structures that are quite different from each other. So now, which one's the best? Well, we want the one with the fewest formal charges. That's the first rule that we would look for. And that crosses this one off the list. Because of the -2 and the +1, we know that one's not a good resonance structure. We shouldn't see a -2 and a +1 when we see other options for our resonance structures that only have one atom with a formal charge. The second thing that we want to think about is that the most electronegative atom likes electrons. So they like to have formal charges that are the minus. So when we look at this, oxygen is more electronegative than nitrogen. So our best structure is this one, when oxygen gets that -1 charge. This one is the worst that we crossed out because of having multiple formal charges. This one is the middle. Excellent. Again, practice problems. You can look at those formal charges, start to identify when things have a formal charge or when they don't, and be able to rank. Overall, N2O is a neutral molecule. Dinitrogen monoxide is neutral. which is the best resonance structure and which one's the worst? Well, we know we have to have at least 2 atoms with a formal charge. We can automatically say this one, when all 3 atoms have a formal charge, is the worst. Then we'll look between A and B and say, well, who should have that negative charge, the nitrogen or the oxygen? The nitrogen should, or the oxygen should, because he's more electronegative. Couple of wrap-up things. These would be conceptual questions when we start talking about bond energies. Now, we presented this at the very beginning of our lecture today. These values that we'll talk about with bond energies would always be given to you. You do not need to memorize them, but we need to make sense about them. What is a bond energy? Well, in a chemical reaction, a bond energy is going to be the amount of energy that it takes to break 1 mole of a bond in a compound. Breaking bonds, again, requires energy. Forming bonds is what releases energy. Now, the overall delta H of a reaction can be estimated. The overall bond energies exchange with a reaction can be estimated by comparing the cost of breaking old bonds to the income of making new bonds. So what we can look at with delta H of a reaction is really just the amount of energy for bonds forming and bonds breaking. And if we know delta H is negative, that's exothermic. This is old material that's still important. If delta H is positive, that is endothermic. Trends in bond energies. In general, what we see is that when comparing like atom to atoms, so carbon-carbon bonds, a triple bond costs more energy than a single bond. That makes sense. There are 6 electrons here to pull apart. There are only 2 electrons here to pull apart. And again, these values would be on a table, but what we would know is that triple bonds are stronger than double and single bonds. Why? Because there's more electrons in those bonds. Again, when we look at that idea, we can start to think about triple bonds are holding those 2 atoms closer together. Their attractions are tighter, and so triple bonds are actually shorter bonds. Than double, shorter than double and single bonds. We can look between single bonds and see some differences as well. If you think about bromine, fluorine, bromine, chlorine, and bromine, bromine, again, the size of the atom getting bigger, what we see is the bond length gets stronger. And when we think bond length gets stronger, we remember our Red Rover discussion, it's easier to break those bonds. So we'll see that the cost is lower. So as we again look at this table, these numbers you would not need to memorize, but you should know that a triple bond is going to be a higher bond energy than a double, and a double is going to be higher bond energy than a single. When we look at the size of the atom connected to a particular element, so going down a group as size increases, bond length increases, and so bond energy decreases. We can use those bond energies to calculate the average delta H of a reaction. We will do this in class. Here is the equation that we will use. Bonds broken is going to be that positive value. Bonds formed is going to be the negative. Making bonds is exothermic, breaking bonds is endothermic. So when we look at this, we can also think about it as broken minus formed. If we want to use this chart up here, these are all the bond energies, the cost for breaking. Now, the income for forming these is just the negative. So you slap a negative on it if it's formed. You would use the positive if it's being broken. Again, covalent bond reality versus Lewis theory. Lewis theory predicted that the more electrons two atoms shared, the shorter the bond would be. We see that in terms of bond length. It's determined by measuring the distance between the actual nuclei of the atoms. In general, triple bonds are shorter than double, and double bonds are shorter than single bonds. We can also look at the size of the atom. Chlorine is bigger than fluorine, bromine is bigger than chlorine, and iodine is the biggest out of all those halogens. The bigger the atom, the greater the distance between those nuclei. The bond length increases as well. So here are some average bond lengths. We see that they should correlate what we thought. Triple bonds are a very short bond. Double bonds are a little bit longer. Single bonds are a little bit longer. These are averaged. Again, you would not need to memorize the number, but you should know the general trend. Here's some trends in bond length. Again, what we see, triple bonds are shorter than doubles. Doubles are shorter than singles. And that's because of the increased attraction with 6 electrons for our triple bond versus our 4 electrons for a double versus just the 2 electrons in that attraction for a single bond. Generally, bond length decreases from left to right across the periodic table. Again, as we go from left to right on the periodic table, atoms' size decreases. And as we go down a column, what we just talked about, atom size increases. So the bond length increases. And in general, as the bonds get longer, they also get weaker, meaning their bond energy decreases. Doesn't cost as much to break them.